Welcome to this introduction to composites materials and composite part design. In this video, we will cover some basics of designing parts with composites material. It includes design, simulation, manufacturing, and introduction to the 3DEXPERIENCE platform for composites. By the end of this tutorial, you would have learned about the basics of composites, composites in the 3DEXPERIENCE platform, Composites Design, and finally, composites manufacturability. Let's get started. First of all, let's define what a composite material is. A composite material is a combination of two or more materials with different physical and chemical properties. These properties complement each other, creating a specialized material best suited for different and specific applications. For example, the resulting material of combining two constituents may be stronger, lighter, or resistant to electricity. It can consist of two or more distinct and mechanically separable components. It can include metals, plastics, minerals, and wood. Different materials can be combined in a variety of ways. The resulting material combines the properties of each constituent material in an optimum fashion. In the context of CATIA composites, we typically are referring to fiber-reinforced materials, meaning a material consisting of a reinforcing fiber such as glass or carbon, which provides the majority of the strength and stiffness, and a matrix that holds the fibers together, like a glue. The matrix, also called resin, is a binder. It ensures the cohesion of the structure. Resin on its own is good under compression but provides little tensile strength or stiffness. Properties of the resin or matrix include supporting, bonding together, and protecting the fibers, transferring applied stresses and loads, imparting toughness, governing surface temperature, the temperature at which the composite can operate, protecting against the environment, UV rays, chemicals and moisture ingress, and helping adhesion to other parts. The main role of fiber reinforcement is to provide strength and stiffness. Fibers on their own are poor under compression, but great under tension. The fibers are packed tightly together and encased in a resin. A well-known example of composites material is carbon fiber composite. In such an example, the reinforcing fiber is made from carbon, which is strong and stiff, and epoxy, a plastic resin that holds the fibers together. Another example would be a polyester resin reinforced with a glass fiber, GFRP glass fiber reinforced plastic or fiberglass. Composite materials, due to their properties, can be used in a variety of parts, like in ships' hulls, sports accessories for motorsports, car parts, or in a fuselage for latest generation aircraft. For instance, composite materials represent more than half of the structure of the most recent aircrafts, such as the Airbus A350 and the Boeing 787. These planes are lighter, so they consume less fuel. The use of composites has many benefits. The purpose of varying matrix and reinforcement properties is to create a material that can exhibit either low cost, low thermal conductivity, lightweight, high dielectric strength, high strength to weight ratio, dimensional flexibility, and corrosion resistance, or any combination of those properties. But there are also challenges with composites materials. One of the main drawbacks of composite materials is that they are not ductile and do not fail gradually. Composites are more brittle than formed metals and thus are subject to direct permanent damage. Furthermore, repair introduces new handling constraints, like the fact that composite materials require refrigerated transport and storage, and have limited shelf lives. Let's see some vocabulary to understand some concepts of designing composite parts or designing parts with composite materials. A carbon composite material is a specific kind of composite that consists of carbon fibers embedded in a matrix. The matrix is usually a polymer resin, for example, epoxy, or a carbonaceous matrix, which binds the reinforcements together. To design a composite part, we use plies. A ply is a flat or curved arrangement of fibers, generally unidirectional, embedded in a matrix component. The geometry of a ply is defined using several contours and a set of zones. A zone is a conceptual definition of a composite part, which represent areas with constant thickness and or laminate. Plies are created from zones. The laminate information of a zone describes the number of plies used for each material and each direction of the part. A variation of the zone-based method is when the zones are defined by and in a grid, and is called the grid method, which is very efficient to design stiffened panels, for example. Those methods use surfaces, outer mold line or OML, to start the design process. But you can also, with the solid slicing method, use a solid. In that case, the solid is sliced to create plies. It is used for monolithic parts or re-engineered metallic parts. Zones are created using geometry and laminate information. A rosette defines the referential in which the fiber direction of plies will be defined. It is computed from a 3D axis system to a given location on a surface of the composite part. The x direction of the axis system represents 0 degrees fiber orientation, and the y direction represents 90 degrees fiber orientation. Finally, the sequence is the manufacturing notion that describes the order in which the plies are created. When creating a ply in a ply group, a sequence is automatically created. The meaning of a sequence is the manufacturing sequence. It contains the plies that can be laid on the mold during the same sequence during the manufacturing process. In the 3DEXPERIENCE platform, CATIA and Simulia apps provide a composites process-centric solution for composites design, which allows designers and manufacturers from various industries to reduce the time needed to design and manufacture composite parts. The main features of the CATIA 3DEXPERIENCE platform solution for composites design rely on various methodologies available to reduce the design cycle time of a wide range of parts and benefit from the integration of different applications to streamline the design process. In the 3DEXPERIENCE platform, you will need to have access to specialized applications for specific design and analysis roles. To learn about composites with academic licenses, you need the engineering expert role and, for FE simulation, the simulation engineer role. Contact your representative or look online on the Dassault Systèmes website for information about commercial roles. The Dassault Systèmes EDU Space website has also related training. The key applications you may use are Composites Insight, to assess and validate the composites design concerning its mechanical behavior using AFEM analysis, Composites Design, Structural Model Creation, to define a mechanical simulation model and mesh, Material Definition, Mechanical Scenario Creation, to define and perform any type of simulation on a mechanical model, and Physics Results Explorer. Composite design starts with material definition. All material data is created, stored, and accessed on the 3DEXPERIENCE platform. Any composite model requires at least one defined material. Users can easily reuse materials from a library or add, edit, or remove material properties from the material database. If editing material properties, these changes may propagate to all referenced models. When creating new material, 4 separate domain types exist: appearance, drafting, composite, and simulation. To model elastic composites, the material definition must contain a simulation domain, along with a composite domain. The composites domain defines the thickness of the ply and other properties used during the manufacturing producibility analysis. The cured thickness is used for the engineering stacking in the CATIA composite model and section properties during Simulia simulations. The simulation domain defines the mechanical properties of the material. Several types of anisotropic elastic behaviors are available, as shown in the top right corner of the slide. The stress-based failure option defines tensile and compressive stress limits in the longitudinal and transverse directions, in plane shear strength, the biaxial stress limit, and if no biaxial stress limit is given, a scaling factor used to define the Tsai-Wu coefficient. The strain-based failure option defines tensile and compressive strain limits in the longitudinal and transverse directions and the in-plane shear strain limit. Before every design, you will need to define the parameters of the composite using the Composites Design application. First of all, in materials management, materials may be added or removed. Materials are stored in the part, but you might need to reroute the material in some cases, like for instance importing a new composite model. Directions can be added and modified as needed. You can even set a color by orientation. You can also add laminate, remove laminate, reorder the stacking sequence, and export or import laminate information in XLS, XLSX, and text format. Finally, you can add a main stacking sequence and a ramp definition. On the 3DEXPERIENCE platform, with the Composites Design application, it is important to define the physical properties of a ply, like the geometry with the contours, the attributes with the material, the ply direction, and the rosette. The contour can be one geometry forming a closed contour, a set of geometries forming closed contours, or multiple. The directions are usually 45 degrees, -45 degrees, 90 degrees, and 0 degrees. All the information relative to the ply is stored and visible in the specification tree. If picking the plies in the 3D is necessary, change the stacking graphic properties to pickable. There are several unique methods for designing with composites materials, helping users create flexible, associative models. Each offers unique benefits to help users easily perform and manage design iterations with a best-in-class ply stacking-based design. First of all, there is the manual approach design. This method is used when the number of drop-offs is low, as well as the number of plies. This approach is the most basic. The user defines each ply boundary and attributes manually. Secondly, the grid approach design. This method is used as much as possible, as it becomes the default method because it includes an excellent framework for the preliminary sizing and design. This method can be used for preliminary and detailed design. It allows users to design in the context of an assembly by referencing interfacing structural elements to help integrate the design and analysis processes. Furthermore, with the solid slicing approach design, this method is used for the cases where the two surfaces OML and IML, inner mold line, are imposed. This method is similar to the grid approach, except the plies are generated based on the volume of a defined solid instead of the ply stack-up definition. This approach is recommended when the final shape of a part is critical. Finally, the grid approach design with import. This method is based on a grid because it has structural reference elements. It is applicable for workflows where the definition of folds exists in a spreadsheet, as it is the case with a wind turbine blade design, for example. In general, this is an approach that is suitable for slender parts. We are presenting each method in specific separate videos. Finally, let's introduce the manufacturability of composites. A large number of composite manufacturing processes have been developed over the last 40 years, including contact molding, compression molding, vacuum bag/autoclave molding, rotational molding, resin transfer molding, RTM, tape wrapping, filament winding, pultrusion, expanding bladder molding, etc. All these processes have several characteristics in common. The reinforcements are brought into the required shape in the tool or mold. Resin and fibers are brought together possibly under elevated temperature and pressure to cure the resin, and the molding is stripped from the part once the resin has cured. The different fabrication techniques can either be classified as direct processes like RTM, pultrusion, or contact molding that use separate fibers and resin brought together at the point of molding, or indirect processes that use fibers pre-impregnated with resin like vacuum bag/autoclave molding or compression molding. Generally, hand layup of fabrics or UD tapes are currently the most common manufacturing techniques. Liquid composites molding techniques are made with software partners like ESI or Convergent. Forming processes are executed with the dedicated CATIA application and software partners like Convergent for HDF. Automated placement processes like braiding, tape laying, or fiber placement are realized with software partners like Coriolis, Ingersoll, MAGFIVES, or MTORIS. In the manufacturing process, it is important to create an associative model specific to manufacturing functions, transfer plies to the tooling surface, and add material excess. To help the operator place the plies on the mold, a document called Ply Book can be created, which is a manufacturing document based on a drawing that provides work instructions to shop floor operators. Finally, it is also capital to run a producibility analysis to identify areas of concern. Performing producibility analysis is an important operation in composites design. It simulates the fiber's behavior of a ply to detect manufacturability problems using the hand layup method. The hand layup process is the most basic and simplest fabrication method for thermoset composites. When a composite part is being manufactured using a hand layup method and the material roll width is lesser than the ply width, the plies are cut into cut pieces based on the simulation results using the splice plies from producibility command. The staggering and overlap parameters play an important role while splicing the plies. After performing producibility analysis, you can perform a finite element simulation using Simulia 3DEXPERIENCE applications, like Mechanical Scenario Creation and Physics Results Explorer. In the case of a composite part, the following parameters are important to study: the stress, the Hashin criteria failure, the strain, the Tsai-Hill and Tsai-Wu stress-based failure criteria, and the thickness of the part. This is the end of the tutorial. In this video, you've seen the basics of composites, the manufacturability of composites, You saw different apps available on the 3DEXPERIENCE platform for the design of composites parts, and you learned about composites design and manufacturability. We recommend, to go further, looking at one of the other videos focused on one of the techniques mentioned: manual approach, grid approach with import, grid approach, solid slicing approach design, and composite simulation.